what it is that you want to take. If in the past I have provided people with a couple of these competition books that that have been recently published, and I can make one available for different teams. But it doesn't necessarily help to take material unless you know what's where, unless you know what problems you want to solve. If you're not familiar with the problem, there's no way you're going to be able to even know that, hey, this is the algorithm to use, this is where I can find it, this is how I'm going to code it up. If you don't know this, it's not going to happen. So that's why you need to work as a team to figure things out. Okay, that's why I'm strongly recommending that you go in and compete this Saturday, so that you have some experience of this. And it's an exciting event. I really recommend that you go and try this out. Okay, any questions? All right. We've talked about this before, but I see a whole bunch of new faces. So let me restate these. There are some enormous problem repositories. You can go to any of these. In fact, VJudge is the biggest one because it combines all these other repositories. VJudge is essentially a portal through which you can access thousands, tens of thousands, hundreds of thousands of problems, and each one you can code it up, submit it, and it'll tell you whether it's right or wrong. Okay? So there's enough practice material, there's enough help for you to prepare for these things. When it comes to the contest, these you can use for training, but then you're on your own. You had a question? Okay. And the great thing is that you can write your program in one of many different languages, submit it, and it'll tell you whether it's right or wrong. Okay? Okay. There are a whole bunch of different topics that need to be covered. These are topics that get covered in the problems. There's dynamic programming. If you've never heard of it, that's a huge class of fairly challenging problems. Then there are a whole bunch of math problems, permutations, combinations, probability, counting, etc., etc. Then you have graph and tree algorithms, things like shortest path, minimum spanning tree, topological sort, etc. Then we have advanced graph algorithms. Then there are geometric algorithms, string algorithms, number theory algorithms, just a whole bunch of other nice stuff. All of these, the more you get exposed to, the better prepared you are. Okay? So I'm going to try and have you look at least one from each of these categories before your November, 19th contest. Let's see how we do. Yeah? There are, as I said before, there are books to help you. The book by Halim, I have a few copies. I'm happy to share it with you for the competition. This is the ICPC one. That's the one in November. Okay, that's also a Saturday. Put it on your calendar right now and make yourself available. Questions before I move on? Yep. No questions. All right. You guys are not very communicative today. All right. Fix the pond. So we're going to talk about a different problem. After that, we'll come back to max sum. All right. So here's the problem. I know it's kind of hard to read, so let me zoom in for the, well, can you read? Yeah, turn around and look at the screen closer to you if you want. Has any of you seen this before? Ian has seen this, no? somebody help summarize the problem for me?
We need to find the minimum number of switches to
Okay.
make the machine be able to.
Tell me
control
more.
the
Tell me.
source.
Give me a little more of the start. What's the setting? What's this pond business? What am I doing with the pond? Ian, you want to help us summarize the problem?
So you've got these gates that you can flip that
Right.
tell you which areas of the pond you can access, and your
Right.
goal is to be able to access every single square on the.
That's right. So your goal is to make sure that every cell of this pond is touched on your path, and you have to set the switches to either horizontal or vertical in order to make it happen. If it's going to sit like this, if the switches are set like this, then you won't be able to go to every cell, right? Whereas if you reset some of these switches as shown as in dotted line, then you will be able to access every cell, and you can make it from and remember, your path always starts here, top left, right, and always ends here at the bottom left. And your job is to make sure that you clean the pond, which means you better visit every cell along the path. And some of these switches, so this particular switch, it was horizontal here, you made it vertical, right? This particular switch was horizontal here it's been made vertical. Then there are others, it seems, that have also become vertical. You can go and see which ones became vertical. In some cases, you may be flipping them back to being horizontal, but your job is to make sure that you can go from start to finish while visiting every possible cell. Yeah.
So would we want to find the switch coordinates first? So for which coordinates?
So the switch coordinates are actually given to you because you're told that there are 2n rows and 2n plus 1 columns, and the switches are exactly. It's annoying, but it's there here.
Odd comma odd or even comma even.
That's right. So A, B are where the switches are, right?
Yeah.
Yeah, and A is always E. What?
Both A and B are either both odd or both even.
Oh, right.
Sorry,
Right. So 1 comma 1 you will have a switch. 3 comma 3 you'll have a switch, or 4 comma 4 you'll have a switch. Sorry.
Yeah.
Did I get that
Yeah,
right?
that's
Yeah.
making sense. That's
Yeah.
right.
So in fact, you'll see that these form nice diagonals, but they're not at every intersection. They're in every alternate intersection, right? So switch positions are given to you, and you either put them like this or like this. These are your only two options, and they pivot at their center like that. So this is the center of the switch. You can either flip it vertical or you can flip it horizontal. Clear? So, how do I make this happen? And then you need to understand what they're asking, right? What are they asking?
Minimum number of switches to be configured so you can go through every
Right,
single
so
step.
how many switches, what's the least number of switches I need to flip in order to be able to get from start to finish and visit every square? Right? Clear? Okay. So what's a naive solution? What's the simplest solution you could think of?
Something I thought of is basically you could take every single gate
Yeah.
that's given, and you can kind of go through like every subsequence of like flipped or not flipped,
Right.
and then test the
That's
grid
right.
to see if every node is reachable.
Sounds good. So you could think of horizontal as say 0 and vertical as 1, right? And you know how many switches there are. you can try every possible binary number that'll tell you the position of each of the switches, whether it's horizontal or vertical, and you can see whether a specific configuration works in terms of reaching your start to finish. And for each configuration, you'll know exactly how many switches were flipped because you can compare it with the start configuration, right? Are you with me about this? Yes? No? You were not too happy. Where did I lose you? Yeah, I am looking at you. You're not paying attention
No,
here.
I am.
Okay, so are you clear?
Yeah.
Okay, good. So give me some feedback. Facial feedback is good. So everyone okay with this? Yeah? Okay. So how many different configurations do I have to try this way?
2 to the number of gates.
Which is a heck of a lot.
Exponential, yeah.
Right, so it's a 2n by 2n by 2n plus 1 grid, which means half the number of rows. Well, in each column there are half the number of things, so it's something like n squared. So even though there are 4n squared intersections, there's something like n squared different spots where there are gates. And each of these could either be 0 or 1, yes? So therefore you have 2 to the power n squared, which is a very large number. And you're told that n can be as large as, somewhere it says.
I don't think the constraints were given.
Yeah, it's not here on this page, but it's there on the next page. So here it says that n can be as big as 300. So therefore, what does it tell you?
Not gonna work.
Forget about trying all possible configurations, right? Because 2 to the 300 is something you're not going to finish this century, right? Okay. So then you're given a description of how the input is given and how the output is given. Here is what the input looks like. This tells you that n is equal to 3, which means that there are 5 rows and 3 columns. Yeah. And this tells you all the flips. Sorry, no, that's not right. It's actually 2n by 2n plus 1. So that's 6 rows and 7 columns. So therefore, the number of switches you have is 3 in each row, and there'll be 5 such rows of switches because the first row and the last row won't have switches, right? And so there are 3 times 5, that's 15 switches. So even if you want to try every possible configuration of the switches, that's too many. 2 to the 15 is a fairly large number. It's somewhere in the range of what? Probably 32,000 or so. Okay. So for 32,000 different configurations, just for n equals 3, we would have to try and figure out which one actually allows you to go from start to finish and touch every square, and then you have to check how many different flips you made, and then pick the one with the least number of flips. That's going to be a pretty expensive operation just for n equals 3, but here you're told n can be as big as 300. So you're in a lot of trouble here. Okay, so the naive approach is not going to take you anywhere. The question is, what do I do?
What if we
want
want
the previous slide?
You want the previous slide? Yeah. Yes, question
What
here?
if we went to the pond and we saw how far we could get and we counted the number of squares? Then we keep track of all the switches and we flip them one at a time to see if our count goes up. And if the count goes up, we keep that configuration and we look for another switch. Just like
Okay,
And we
so
keep doing
you're
that and hopefully-
suggesting to start with something and then try to increase the number of squares you visit.
Yeah.
So for instance, over here, you're visiting 3, 4, 5, 8, 11, 14, 17, 20, 22 squares, and then you're gonna try some flips to increase this. Okay, so that's a strategy that says, let me start with a path that visits only 22 squares. I have a few more squares to visit, so let me try some flippings and hopefully it'll increase things. The question is, how do I know it's gonna increase? How do I know I'll find a switch that will increase it?
You'll have to check.
What if
each
everyone,
switch.
what if everyone goes down? Some of the switches will actually decrease the number of cells you can reach.
So if it goes down, we don't do it. If it doesn't, we try it.
If it stays the same,
We try it.
if it stays the same, you wanna
We
try it?
We keep that configuration as a configuration to keep trying.
Uh-huh. Okay.
But yeah, maybe it ends up being worse than Dion's solution because
Well, the problem is how many such things are you gonna have to try, right? If in the end you're going to end up trying 2 to the n squared, then you're in trouble,
yeah.
right? And if something doesn't work, are you going to backtrack and put it back as what it was, or are you going to move it further down the road and say, I'm gonna give this a try, and then try something else, and then maybe 3 steps later you realize that none of this is working? Then how far up the chain do you have to go and backtrack? And if you do that, then you're going to run into this exponential search process. So you need to think about this more carefully, right? Any other suggestions? Osman, you're ready to tell me something.
I mean, not really. I was thinking about focusing on the squares that are actually closed.
Uh-huh, okay. There are
Yeah.
some squares that are covered in all directions. You can't get that, right? Where is it?
Like these here.
Yeah,
This.
like that, like this piece over here. There's no way to get there from the starting configuration unless you change something.
So I was thinking about dealing with those switches, but I'm not really sure how you're going to be
Uh-huh.
able to
Yeah.
kind of manipulate.
So first of all, there are too many switches. You don't know which switch to throw up or down. And there are switches where it could go up. There are switches which would reduce the number of squares you visit, and there are others where it stays the same. So we don't know how to go and systematically try these switches. Yeah.
An idea I had is that initially you can just pay attention to cells that are reachable, like without having to make any switches.
Uh-huh.
And then we can.
Right. So I can find a path
Yeah.
here.
And then like.
I don't really know how to do this, but let's say I know how I can figure this
Yeah.
out. Okay.
And then using some algorithm, we can evaluate like how many locked regions there are, like of
Yeah.
unreachable cells.
Mm-hmm.
And I don't think we're going to need more than one switch to access those regions.
Uh-huh. Yeah. Okay. Well, I'm gonna have to hold your thought and let other people catch up.
I was gonna say something, so what if we try to draw what squares are connected to what other squares?
Yeah. So we know that there are only 2 possible states for any switch. So this switch here, for instance, is vertical. Well, actually, let's look at a different switch. Let's look at this switch here. This switch is horizontal, right? Now, there are 4 squares around this switch because this switch is centered right there, right? There are only 4 squares around it. And can we say something about how those squares are connected? Meaning, which square can I go to from which other square? Right? So what you'll see generally is that if it's horizontal, the top 2 squares are connected, the bottom 2 squares are connected. If it's vertical, then the left 2 are connected and the right 2 are connected. These are your only 2 possibilities. You can't have it sitting in the middle like that, right? So either the top 2 and the bottom 2, or the left 2 and the right 2. These are your only 2 configurations around each switch. Now, is that of any use? All right, and those are the things that we're going to investigate further. So this is the same picture we had before. I know I always have to start here and finish here. That's given, right? I know that every switch can be horizontal or vertical, and I've colored them in such a way that you can see that in this case, I've flipped that switch. I've flipped this switch here from horizontal to vertical. And then there are two others here, that's this switch and this switch that got flipped. And then there were two others here, that's this one and this one that got flipped. So this switch went from vertical to horizontal, all others went from horizontal to vertical. And now I see that I can visit every square and get to the endpoint. Right? So our job is to figure this out.
So I can see there that we have like 6 switches, but in the output, they say there's 4.
Uh-huh. So you could have done with 4.
Yes.
That's right.
Uh-huh.
You're absolutely right. So it's not the best answer.
This is not the most.
So even though some of the configurations might allow you to go from start to finish, you also have to look at how many got flipped and keep track of the best one. So that's another little minor detail to keep track of. Any thoughts? Where should I go from here? So let's follow up on Nimi's idea earlier, saying how can we talk a little bit about what's connected to what? Now we said a couple things earlier, and let's follow that up. So imagine now that I have a big pond, right? I'm zooming in and looking at some little portion. The switches look something like this, the red dots here, right? So every switch, at each switch, either there's a horizontal one or a vertical one. I've just drawn all the configurations here. I've just drawn the grid here. And let's say I look at the center switch point. Now, what I know is that either the switch is vertical or horizontal. So there are only 2 possible states, either this way or this way, right? And in each case, I know what the connectivity of the neighboring cells are, right? So let me show that with a picture here. So if I look at this, I'll just give the cells names A, B, C, D, so that we know what we're talking about. And what you'll see is that if the switch is vertical, then A and C are connected and B and D are connected, right? That's what my path is going to allow me to do. And of course there are other cells here, but in order to use this cell, I have to either get here from E or from F. Those are the only 2 places I can get there from, right? I can't get here from there, so therefore it all depends on how this particular switch is positioned. If it's vertical, then I will come from F. If it's horizontal, I'm coming from E. Clear? So what you'll see is that for every cell, there's only one place from which you can come and one direction you can go to. All right? And this turns out to be significant in the way we're going to analyze this. What do I have here? What am I trying to do now?
The EF switch came
Oh yeah, the EF switch came off, or it's if it's horizontal, but this I already told you, right? If it's horizontal, you're coming from E. If it's vertical, you're coming from F. So that means every cell has at most 2 neighbors at any given time. Once you've set the configuration of the switches, every cell has only 2 neighbors. Therefore, the path, if it's going through that cell, if you're ever going to visit that cell, it's very clear which ones are the neighbors on the path. Okay? And this turns out to be important because now, also before we go to the next step, let me talk about what happens when you flip a switch. So here, let's say that A is connected, so let's say this is vertical, right? I'm not sure what my picture is trying to do. Okay, right. Yeah, so here's what I'm trying to say. Let's focus on the cell we've called labeled as A. If the neighboring switch here is vertical, then A's neighbors are C and F. If this switch is horizontal, then the neighbors of A are C and E. Okay? So at any given time, it doesn't matter what the situation is, once you've set the configuration of the switches, the neighbors of A, there are only two of them. Okay? Which means that if you came in from one cell, you have to go out of the other cell. All right? So in terms of a path, it's fixed. You don't have any choices. It's not like I can come here and decide whether to go this way or this way. You're never gonna have that choice. It's always going to be, I came in from here, I have only one other way left, and that's how I'm gonna go. Here's what that means. This has an implication because now every cell only has two neighbors once you've decided on on the switches. Now if you look at it, I have a start point in my whole grid. That's the top left, right? I also have a destination, which is the bottom left. Now, if I start at the top left, that top left is not going to have two neighbors because it's a border location. So it has only one way to go. I don't have a choice. It all depends on how that first switch is. So if you look at I can show you back that picture from, come on, too many flips. So if you look at this one here, if this switch is horizontal, there's only one way for me to go. I don't have a choice. I can't go any other way. And if this were vertical, again, I have only one way to go. Now, if I came here from there, then my only way I can go is continue this way because I have no other choice. Once I get here, this is the only other neighbor, so I have only one choice. So therefore, I have to keep going this way because every cell, other than the start point and the end point, has two neighbors, exactly two neighbors, one from which you come in and one to which you go. So therefore, if I'm coming into a cell, I have a way out, and there's only one way out. And so I keep doing this. The only place I'll stop is the green spot because there is no other place I'll stop. Because everywhere I come in, I'm going to have a way to get out, right? So therefore, what does this tell you? What did I just argue?
If you're connected to a cell that's connected to someone else, then you have a path all the way around. If every cell is connected to two cells that are connected to other cells.
Right. What I'm saying here is that we already know every cell has exactly two neighbors under any configuration.
Except the first one.
Therefore, except the start and the finish. Therefore, if I start at the start, I have to be able to go to the finish because if I go from there to any other cell, then there's only one way to go. Only one way to go. So I keep going until at some point I have to stop. At no point will I have no choices or two different choices. I'll have exactly one choice, and therefore I have to end here. Therefore, my first path will always be there, except that it may not touch all the cells. Should I repeat this?
Yeah.
What we have here is a situation where every cell has exactly two neighbors, okay, except for the start one and the end one, which has only one. So if I start at the start, it has only one neighbor, but if I go there, it has exactly two neighbors, and so therefore, if I come in from one, I know where to go. My destination is fixed, because I can't go back to my old cell, right? So if I'm coming from here, and this guy has only one other neighbor, I will go there. I get here, I came in from there, there's only one other neighbor, so I go to the neighbor. And I keep doing this, and every cell I visit has the same property. If I'm able to come in, I should be able to go out. If there is a door that let me in, there is a door that will take me out, except the last one. So the only place I can stop is the green spot. Is this clear? Yes? So therefore, we have a start path that always takes us from start to finish, except it may not be the right path. It may not touch each cell. Is there anyone here who didn't understand that part? Because this is critical. You need me to repeat anything?
Are you saying this is even before we we flip
Even
any
before we
switches?
do any flips, it doesn't matter
Can
what
you-
situation of the thing it is.
And that's true even for,
It's true for any
oh,
configuration.
you're saying I may not traverse every cell though?
I may not traverse
Okay.
every cell, but I can get from the start to finish, and so that's never going to be in question.
Okay.
Yeah? I will always have a path from, think of this as your entry into this cave, yeah, into this maze. It says that you will always get out, because you never have a choice. You're never going to get to a spot where I say, should I go left or right? That'll never happen, because you'll come into a room through one door, and there'll be a different door that you can get out of, always.
So are you saying that we don't need to check the path, that we can just check the configuration of the switches?
Well, I'm establishing one thing first, that is, there always is a path from start to finish, regardless of the position of the switches. So I can go and flip anything I want. It's not going to mess up the fact that I can get from start to finish. Are you okay with this?
So what property is ensuring that there are no dead ends?
Because the degree is 2. So this is a graph property. If you've taken the discrete structures class, it'll immediately connect. If you have a graph where every vertex has degree 2, then, and there are exactly 2 vertices with degree 1, then there's a path from one to the other. Okay? The problem here is that it may not touch every cell. And that's because what? Why are you not able to touch every cell? Because there are cycles here.
Oh.
Okay? And this is what we need to talk about next. All right, so let's get back to here. Oh, what happened here? Oof, my animation is all messed up. Okay, fine. So what we've observed is that there is always a path from the start to the finish. We agree on this. Next, we are saying that this path may not visit everything, and the reason is because there are portions that are just cycles. Remember, in a cycle, every cell has 2 neighbors, right? Because on a cycle, each one has one neighbor before and one neighbor after, right? So cycle is okay by itself. It doesn't hurt anything because everything has 2 neighbors. But it may be outside of this path. So therefore, what it says is that if I look at the connectivity of the cells here, it's going to look like the following. There's going to be one beautiful path from start to finish, and there'll be a bunch of these disjoint cycles. And why is it a cycle? Why is it a set of cycles? Because every vertex has every cell has 2 neighbors. Right? Otherwise, if you have more than 2 neighbors, then it'll start to branch out and do crazy things. There's no branching anywhere. You're not allowed to branch. So therefore, this path cannot go and touch itself again. It's not allowed, because then you will have a vertex which has 3 neighbors, right? Same thing, you can't have a cycle, you can't have 2 cycles touching like this. That's not gonna happen, because that vertex which is part of both cycles has degree more than 2. Therefore, it has more than 2 neighbors. Not allowed, right? So it's key that every cell has exactly 2 neighbors, regardless of what the switches are, how you place the switches. So that's what's important. And then the last bullet says, if you flip some switch, something crazy happens. But that path will still be a path from start to finish. It may change, but it's still a path from start to finish. Okay? Now the question is, how do things change when you flip a switch? That's what we need to understand. Are you clear? Somewhat?
Mhm.
So, this is what we have right now. Here's the current situation. What if I were to flip a switch? Doesn't matter which one. We need to know what happens to the things. Okay. Now, it's important to understand that there is one path and a bunch of cycles. Clear? When I flip a switch, something is going to change.
Should disrupt the cycle.
It's going to disrupt the cycles. So let's look at how it disrupts. So here, I flipped that switch from horizontal to vertical. And what happened? Well, the path changed, but it still goes from start to finish, right? Then some of the cycles got disrupted. Well, this cycle and this cycle didn't get disrupted. This cycle didn't get disrupted, but this cycle here disappeared, right? It became part of this path. And so every flip of a switch will change this configuration. And our job is to find which ones will do the trick for us. Because in the end, what do we want? We want what?
Touch every cell.
We want a path from start to finish.
That goes over all the.
Well, if it goes over all the cells, what happens to the cycles?
They disappear.
There are no
No
cycles.
cycles.
So we have to slowly make the cycles disappear. Question is, how do I make these cycles disappear one by one? Or maybe more than one at a time, who knows? Right?
You could form a cycle by flipping a switch too,
Ooh,
right?
yes, so for instance, this switch is currently horizontal. If I make it vertical, what happens?
Two cycles.
I suddenly formed 2 cycles from one.
Mhm.
Okay? What if I flip this guy here from vertical to horizontal?
Reduce it.
Those 2 cycles became one bigger cycle, right? But look at what's happening. I always have one path and a collection of cycles. And that's because every cell has exactly 2 neighbors, except for the start and finish. Otherwise, this is not true. Okay? So now, it turns out the algorithm is not so bad, but first, what's important here is that we've modeled this like a graph problem. Okay? How many of you have never heard of graphs? Okay, good. So this is modeled as a graph problem where every cell has 2 neighbors, right? And we know that there is a path that goes from the start to the finish. No problem, it always is going to be there, regardless of what you do with the switches. And along with it, we have a collection of cycles. So therefore, the graph of connectivity that we drew with the squiggly lines always looks like this. It looks like there is a path from start to finish, and there are a bunch of cycles. We'll call this as property Q. Okay. The big question is, in the end, we want a path P and no cycles, right? That's what we really want. And so we have to figure out how this happens. Now, flipping a switch can change the number, change the path, but the property still remains correct, right? And so what we're going to say is that when you flip a switch, the number of cycles may change. All right? In fact, it's true that the number of cycles will always change. Right? And so that's our job, to understand which ones will change and which ones will increase, which ones will decrease. We want to go from whatever number of cycles we have all the way down to 0. Okay, so we have now said every flip increases or decreases the number of cycles by 1. So here is the algorithm. We'll call this the greedy algorithm. Our job is, we'll take our grid, we'll find all the, we'll set the switches as they are. In fact, we're already told what the initial setting of the switches are, right? For the initial setting, we'll figure out which cells are connected to which other neighboring cells. We take all those edges, it'll look like a graph. That graph, we already know, simply is one path and a collection of cycles, right? So therefore, this graph that connects all the cells is simply a path and a collection of cycles. We will count the number of cycles we have in this graph. And remember, all the cycles have to be disjoint. You can't have them touching each other, right? We know this already. So we have, let's say we have C number of cycles. Then we'll look at every switch that decreases the number of cycles by 1. If we find such a switch, we go and switch it. Well, we go and flip it. And we reduce the number of cycles by 1. Okay? We keep doing this. Eventually, it'll become 0. Right? So, the question is, how do I find such a switch? If we can find it, no problem, we'll flip it. And the key question, as I said, is how do I find such a switch? Should I throw back the other picture?
Well, since we know how to count the cycles,
Mm-hmm. Yes.
why can't we throw a switch that's located, that is creating a cycle? And we count the number of cycles after we
There is,
flip.
well, so I don't know what it means to say, because this cycle, for instance, has 4 switches around it. I don't know which one to throw, right? I don't know which one is going to work, which one is actually going to reduce, which one is going to increase, I have no idea. So one possibility is to go and try every switch and figure out whether it increases or decreases. And hopefully we'll pray that we find one that decreases.
It's not about this. I just want to ask, what days do you guys do this?
Later, please. Yeah, let's think about this.
Because
right?
I have to go right now.
Then
so-
I'll send you an email, right? So
Okay.
email me by Discord and I'll
Okay.
reply to you. Yes.
Thank you.
So what do I do here?
So as we're walking, if we encounter a cycle, maybe we open the switch, we move it, and we go there inside, and that's how we
Well,
the cycle.
so say again, start again.
As we're walking
Yeah.
through the graph,
You mean the path?
as we're walking through the
The
path.
path,
uh-huh,
yes.
if
Mhm.
we encounter a neighboring cycle, that
Uh-huh.
we can move the switch, and then we
So,
go in.
so
that
for
makes the-
instance, I'm here.
Yes,
What am I doing?
except for the
Start.
the start, yeah.
Okay, fine. I'm here, and then
We don't open.
I don't
it.
do anything.
No, because we'll be going back.
okay. Well, I could have flipped this, and then I would suddenly get like that. No.
Yeah,
Something like that.
it could work because it's
It
the
could
same
work.
thing that we did before.
Yes, I know.
Yeah.
So we need a clear rule for, well, first of all, we have to convince ourselves that there always, you can find a switch, and then we have to talk about how to find such a switch, right? Once we do that, we're set, because we just keep finding these switches, flip them, and we're done, right?
Is every cycle always gonna have 4 switches?
No, there are ones where there are more. This one has
4.
well, there's one inside, so 5 really. You mean on the border?
Like what
it could
causes
be-
the cycle?
It could be worse, it could be strange.
There's
Um,
3 on the other one.
So for instance, if I flip this vertical like, if I make this horizontal and if I make these two as horizontal, then I will just get one big cycle like that, and it'll have 1, 2, 3, 4, 5, 6, 7. So that.
So you have to evaluate as many as.
We don't know. Yeah, we can make even stranger situations, I'm sure.
So
Right?
every cell is guaranteed to have a switch adjacent to it, which means that we
That's
only have
right.
to find the ones that are next to another.
In fact, every cell has exactly, no, some of them, well, it can have 2 switches around it, yes, so.
So the bottom one is a good example, like we can't flip the one in the center, but we
Uh-huh.
can flip any of the other ones on the edges.
Yeah, but how do I know which ones? So I mean, it looks like I have to go and try every one. And there are n squared such switches. So I'll go and try each one and then find one that reduces the number of cycles. Is that?
I don't think it matters which one you flip.
Well, but maybe there's only one switch that reduces the number of cycles. Because remember, we want to find one that reduces the number of cycles. Okay, so you guys all have pretty much the idea, but there are 1 or 2 small pieces that are critical. So we went through this, we said we'll start with a graph, find the connectivity. We know it's going to have one path and a bunch of disjoint cycles, right? We know this. We'll count the number of cycles somehow, we don't know how, but let's just assume we know. And we'll find a switch and flip it. And then we'll just report the number of flips, okay? Because each flip should reduce the number of cycles. We're only picking flips that reduces the number of cycles by 1. So therefore, we know the exact progression from C to 0. We know how many flips we will make, and at the end of it, we'll just report the number of flips, right? The problem is that switches could be all kinds of things. Switches could border the path and some unreachable cells. Or a switch could be between 2 unreachable cells. Or it could be inside an unreachable cell. We've seen examples of all of them, right? So we don't know which one to pick. But assuming that we can always find a switch that reduces the number of cycles, we're going to be great. And so this is where we see that in the best case, we're going to always reduce the number of cycles, right? And so therefore the number of flips is exactly the number of cycles. Correct? So if we can prove that we can always find such a switch that reduces the number of cycles, we're done. Because we can report this answer without actually going and finding the flips, right? So therefore, all this stuff here, we can throw it away because I don't need to look for switches. Once I know the number of cycles, I just report it.
But you gotta know which ones to flip.
I don't need to know that because they're only asking me for the number of switches. But how do I know this will work? How do I know I'll always find the switch that reduces it?
An idea I had is that for any gate that borders a cycle, since what you said is that like regardless of which,
Borders a cycle, that's dangerous, yeah.
you said that regardless of which flips we perform, that path will still exist.
Correct.
So if
You're not gonna hurt the path, but it may change.
Yeah. So and if we flip those such gates, then we know that
Okay.
those cells become reachable and
Good.
that there's still a path from the beginning to the end.
Okay, good, but you missed a couple of keywords, but you're absolutely right. So, where did I put that?
What did you?
So, yeah, I'm gonna repeat that in a second. Where did this go? Yeah, so what he's saying is the following. Let me go to the examples because then it'll become clear. This is the path we have, right? And Lorena actually mentioned this already, but here's what I would do. As I walk along this path, I see if there is a neighboring cell that I cannot reach. In this case, yes, there is. So immediately I'm gonna flip the switch. Now if I flip the switch, what happens?
It brings it-
This path now will go like that and like that. Number of cycles reduced by 1 because this cycle got eaten up by the path. Right? Remember, this switch made sure that this was a cycle. So this is its neighbor. So if you're gonna get in here, you go through the cycle, you'll end up there. And therefore this will be connected to that, and so therefore your path will continue, right? So I know exactly which switch to flip, that one. Then I walk down here, everything here was all accessible, everything is fine. When I get here, I see that there's a neighbor that's not reachable. Flip that guy, yeah? So this becomes horizontal, and now I'll go like that.
Why didn't you do that at 2?
What do you mean at 2?
Like when you.
I did that at 1, that's good enough, no?
No, when you came down and you went up.
So I was supposed to go like this, but right here I found a neighbor that's not reachable, so I went down this way because this flipped.
Right.
So it goes this way. Let me draw
And
it
then you
actually.
take the right.
Let me draw it so that everyone gets it. Yeah? All right. Whiteboard. Yeah. Okay. So I'm starting here. Instead of going right, instead of going right, I'm going to flip that switch. So this thing is going to get flipped to vertical, right? And so therefore my path now becomes like this, right?
Right. Now you turn right.
And now, when I'm sorry, I go up there, and again I have to go down, because again, the neighboring cells are all reachable. Okay, I can go and mark all the cells as reachable. I can just walk down my first path and mark all the cells as reachable, and I know which ones are not reachable. Is there a neighbor that's not reachable? So far nothing, right? And then I come down here, and I turn around, and here I see a neighboring cell that's not reachable. Oh, sorry, even here, no, all this was clean, right?
The switch between, at 3.
Forget switches, I'm walking on the
No,
path.
I'm pointing to that cell to the left of that
So,
one.
well,
Right after
I
2.
came down here like this.
At 2.
Yeah,
That's-
this one is reachable, what's the problem? All these are reachable cells. I'm not gonna worry about reachable
Okay.
cells, I'm only gonna worry about
Okay,
unreachable
when you
cells.
say reachable or not, you're looking for.
Meaning
whether it's
somewhere
inside a cycle.
along my path it's there, so I can reach it, right? All these are reachable cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all these are reachable, all the way up till here.
Okay, got it.
All these are unreachable cells on this path. So over here I encountered my first cycle, first cell that's unreachable, therefore I flipped it. So that was the first flip, and now I do a second flip, and the second flip will now force me to go horizontally, like that, and like that, and come down here. And over here, I will encounter the next neighbor that's unreachable. So I'll flip that switch. So, sorry, I forgot to mark this guy here as horizontal, right? And now I'm going to make that horizontal guy as vertical. So it's gonna look something like this, I don't know. Did I get this right? Yeah.
Yeah.
Something like that, okay? So therefore, my path is going to go down all the way around, and then here I'm going to, when I'm here, I'm going to encounter this guy that's not reachable, so I flip that. So therefore that vertical switch will become horizontal, and yeah, so it'll go like this. So this switch is going to look like that. And so now my path becomes, we'll continue like that, we'll go like that, and then go like that, and it'll end up over here. You should work that out and check. I hope I got it right. Right? So how many flips did I make? Easy, I marked them all. This was a flip, 1, 2, 3, 4, which is exactly the number of cycles I had here. 1, 2, 3, 4. Each cycle needed 1 flip. I didn't have to actually do this work. I could just count the number of cycles and report it. Clear? So in the end, it becomes a graph problem. For every cell, I figure out who its neighbors are. I create the graph. I find the path, I find the cycles, and report the number of cycles, and that's my answer. Yeah?
I had a question. How would you solve this if it was to find the shortest path that touches like all the tree?
Shortest path is different, right?
No, to find a path that touches all the cells in the grid.
It is touching all the points in the grid now.
There is no such thing.
Wait, how do I
All the paths are gonna be.
Wait,
the same.
I'll think about it. I'll think about it.
Okay, think about it. Everyone clear about this? Okay, well, how do I find the number of cycles?
From the patterns of the switches.
Patterns, ooh. But I have to do some computation. What do you mean patterns? I don't understand that.
So going back to my idea about first, like, considering the original path as it is with, like, the original orientations,
Mm-hmm.
you're going to be, like, given that will compute a list of cells that were reachable, and then you can.
You should
go-
assume this is what you started with.
Yeah, and then you go through the grid again, except you consider, like, all points that weren't touched by that path, and then you can perform something like a BFS on each cell that comes up as, like, unreached, and then mark that as reached, and all of its neighbors as reached.
Yeah, so you're going into the details of the algorithm. The way to think about it is, what canned algorithm are you going to use? Tell me that.
BFS.
BFS needs to be enhanced. BFS will only go and visit everything. It won't tell you how many cycles. So it's really called connected components, the number of connected components. And that's the algorithm you need. But you're right, you're absolutely right. Yeah, is that clear? So if you go back to your graph algorithms material, there's a simple algorithm that'll find you the number of connected components. Essentially, you can either do depth first search or breadth first search, it doesn't really matter. You start from a vertex and do one of these searches, it'll go and visit all the vertices that are connected. If you start with this guy here, what will it get you? It'll only get you the path and nothing else, because nothing else is connected, right? So you would have found one path, you set that aside, then you say, okay, now I'm going to restart the search. Restart either breadth first search or depth first search. It doesn't matter where I do it from. If I do it from here, it's going to find me that. If I do it from here, it's going to give me that. So the number of restarts of breadth first search is what I need to report. Okay. So you have to modify breadth first search in order to make this happen. It tells you the number of restarts, which is essentially the number of cycles. Okay. Anyone didn't understand that last part? Because that's the key part. If you don't ask, it goes.
It's the one in your algorithm where it's gray. If you go to a cell that's already marked gray, because
No,
it's been visited
that's
before.
later. That's later. Here, this is the first part where you're counting the number of cycles. Where did I go? See here? No, the algorithm. Remember, all the rest got X'd out, right? So what does it say? First, you have to construct this graph. constructed the graph, I know exactly which vertex is reachable from which other vertex. Remember, every cell is a vertex. I'm finding out which ones are reachable based on the position of the switches. Then I run breadth first search starting from the top left. That'll give me this path because there is nothing else that it'll find. And then I have to figure out how many times I restart breadth first search. Each of those restarts will give me one cycle. And then I get the count and I just report it. Okay? So I'm not looking for neighbors, I'm not looking for unreachable cells, none of that stuff because I didn't need it. All that goes away because all that is not necessary. Correct? Is this clear? So in order to count the number of cycles, I have to run breadth first search repeatedly and count the number of restarts. Okay? You guys have to get more interactive, otherwise this session is a waste. Seriously, I need you guys to think more. By the way, at 5 o'clock we're starting a new club called the AI Engineers Club. So if you want to stick around and enjoy that, you're welcome to do so. Any questions? Oh yeah, I forgot to talk about time complexity. Remember, you are running either get first search or breadth first search. Each one is order of m plus n, where m is the number of edges. The number of edges in this whole graph is still big O of n, and so you can report the number of connected components in big O of n time. And that's the nice thing. And then if you're asked, by the way, if you're asked to find the exact switches to flip, how do you do this? Sorry?
So that's what I wanted to ask.
I already answered it,
Isn't that
but
what
yeah.
you just talked about?
Exactly, yeah. So you start on the path, and then as you walk along, look at the neighboring cells. If anything is unreachable, bang, you flip a switch there, right? Remember, if two neighboring cells, if one is unreachable, it's because there's a switch. Whatever that switch is, flip it, right? If it's horizontal, make it vertical. If it's vertical, make it horizontal. That's it. And suddenly that thing will be reachable because it's a neighbor. And we discussed this. There are only two possible things that can happen. Two cells that are neighboring on the grid, they're either going to be reachable from each other or going to be unreachable because of the switch, at least directly, right? So I can always find that flip switch, and in fact I can do the whole thing in big O of n time, even if you ask me to report which switches I have to flip. And I challenge you to write this up because it's all just depth first search, it's straightforward, right?